All right, so let's knock out naming of molecular compounds. Let's remind ourselves what molecular compounds are. They're formed when atoms share electrons to form covalent bonds. Form covalent bonds. So this differs from ionic compounds where they're formed from ionic bonds and the transfer of electrons. Covalent bonds are formed through the sharing of electrons. And so remember how we identify molecular compounds. They are formed when all of the elements in the formula are nonmetals. And so molecular compounds also have some typical properties, such as they're typically gases. They have low boiling points, gases at room temperature, and low, if they're solids, they typically have low melting points. So I have some examples here of molecular compounds: H2O, CH4, and all of these examples, these molecular compounds, they're all formed from nonmetals. They're all elements on the nonmetal side of our periodic table, and they're formed, if we actually drew out the structures, they're formed through the sharing of unpaired electrons with adjacent atoms. All right, so in an example here, we have two hydrogen atoms, each with one proton and one electron. And so when two hydrogens atoms come together to form a hydrogen molecule, you can see essentially we're taking these unpaired electrons and putting them together to form and sharing them to form that covalent bond that holds that molecule together. Okay, so let's talk about naming of these compounds. Again, the big picture here is, can you identify ionic compounds versus molecular compounds? Molecular compounds, remember, are all nonmetals in their chemical formula. Oh yeah, remember, all molecular compounds are composed of all nonmetals. Sorry, I wrote it twice. But that's okay, because it's just that important. There are different rules when it comes for naming molecular compounds. So the first thing is, if we have a molecular compound that has no hydrogens in it. So let's do those rules first. For naming, let's like these two examples. The steps to naming molecular compounds with no hydrogen is, first you want to name the first element with a prefix that indicates the number of atoms that are present. So this differs from ionic compounds. Ionic compounds, you never indicate number of atoms, but in molecular compounds, you do most of the time. So you name the first element with a prefix indicating the number of atoms, unless it's mono. Mono meaning one. So if it's just one atom, like in both of these cases where the carbon is first and there's only one of them, you actually don't put the prefix. So, but we do for all other cases. And then you want to name the second element with an "-ide" ending and indicate a prefix indicating the number of atoms. So what do I mean by prefix? Do I have it here? Yeah, so here are the prefixes. So if there's one atom present, it's mono. Two, di, tri, tetra, penta, etc. All right, so those are the number of atoms and their related prefixes that you want to use. Right, and this slide actually kind of summarizes the naming for molecular compounds. But let's go through these two examples first. So first step here, name the first element with prefix indicating number of atoms unless it's mono. So carbon here, there's only one carbon, so we would have written monocarbon, but remember, you don't add the mono for the first element, so we just write carbon. And then you name the second element, so in this case oxygen, but with an "-ide" ending, and a prefix indicating the number of atoms. So in this case, there's two oxygens, so this would be oxide, but we want to indicate number of atoms, so this would be dioxide, carbon dioxide. So you, I'm sure, know what carbon dioxide is. That's the stuff we exhale, carbon dioxide. So it's the second element gets the "-ide" ending, and you always indicate prefix unless it is mono in the first element. All right, and then second example here, so we have just CO this time. So carbon, there's only one carbon, so it would have been monocarbon, but we don't put mono, so we just put carbon. And then we have just one oxygen. Oxygen becomes oxide, and then now we need to indicate how many oxygens there are. So there's only one, so this would be monoxide. carbon monoxide, the deadly silent gas. So you might be thinking monoxide, shouldn't it be monoxide? So because there's a double O, we just drop one of them, so it becomes monoxide. They share the same O. All right. Okay, so let's do some more examples. So this slide kind of summarizes what I just said, how to name binary molecular compounds that don't contain hydrogen as one of the nonmetals. So again, it's you name the first element in the name, then the second. In the first one, you always indicate the prefix unless it's mono. So here I wanted to note, do not include if it's mono, if the prefix is mono in the first element. And then in the second element, you always change the element name ending to "ide." And then you always include the prefix, no matter what. Always include, always include. So our exception with the mono thing only is applied to the first element. Okay, so let's go through these. All right, so first one, name the first element, sulfur. So sulfur, there's only one, so we just write sulfur, not monosulfur. And then the next element is fluorine, and there's 6 of them. So fluorine becomes fluoride, and then there's 6. So if we look at our list here, 6 is hexa. So our prefix is hexa, and fluorine becomes fluoride. So it's hexafluoride, sulfur hexafluoride. And again, in all of these examples, all of the elements in the molecular formula are nonmetals. Okay, so our next one, PBr3. So P is phosphorus, and there's only one, so we don't have to put monophosphorus, it's just phosphorus. Phosphorus. And then we have bromine here. That's our second element, so bromine becomes bromide, and there's 3 of them. So it's phosphorus tribromide. I always think molecular naming is easier because it's just very straightforward. Just like look at the elements, say the number. Okay, so now we have N2O5, so nitrogen and oxygen. Nitrogen here, we name the nitrogen and the prefix. So in this case, our prefix is 2, so it's di. And this time we finally get to include one because it's not mono. So since there's 2 nitrogens, we say di nitrogen. And then we have oxygen as our second element, so that gets the "ide", becomes oxide, and there's 5 of them, so that gets a prefix of penta, penta oxide. Dinitrogen pentoxide. Actually, yeah, it's pent. Usually we drop the A, pentoxide. But if you put pentaoxide, I'd be fine with that. But I think IUPAC naming goes with pentoxide. Okay, next, silicon and oxygen. So silicon, we just name that. It's mono, so we don't include it. Silicon. Oxygen becomes oxide, and there's 2 of them, so it's dioxide, silicon dioxide. So also note, so SiO2 looks similar to CO2. And remember how we named CO2? That was carbon dioxide. And so you would expect that SiO2 would have, kind of a similar structure and name, so silicon dioxide. So you can kind of draw comparisons there. All right, and our last one here, CCl4. So our first element is carbon, 1 carbon, so not monocarbon, just carbon. And then we have chlorine, our second nonmetal. So chlorine becomes chloride. There's 4 of them, so it's tetrachloride. So always remember, in molecular naming, you do indicate the number of atoms present. So that's like the big difference from ionic compound naming. But again, remember, you have to be able to identify when given a molecular formula, is it ionic or is it molecular? Ionic compounds need to have a metal in it for cation to form. In molecular compounds, it's all nonmetals. Are we going to do more examples? Oh no. So now, so that was molecular compounds without hydrogen. So now let's think about naming acids. So now let's tack on hydrogen. how do we name a molecule that has a hydrogen in it? So when some molecules have hydrogens in them, we typically call them acids. Acids will have a generic formula HX. The reason we write this is because an acid is a molecule or ion that's capable of donating a proton, or essentially an H plus ion. An H plus ion is a proton. So when I say or proton or hydrogen ion. So we will work with acids in lab. So it's important to be able to name them and identify them. Acids have a hydrogen in the molecular formula somewhere. So some acids that we will use and interact with include HCl, HBr, H2S. So these we call binary acids because it's hydrogen. It's an acid because it has hydrogen in it and a nonmetal in it. So hydrogen also is a nonmetal, so that's why we kind of group acid naming within molecular naming. So these are all examples of binary acids because it's just hydrogen or hydrogens tacked onto a nonmetal. So to name a binary acid, just one that has, like one element attached to it, we add a hydro prefix to the other element that is there, and then replace that nonmetal name with ic acid. So that we don't actually name the hydrogen anywhere. It's implied because we're saying it's an acid. So these names, so this is the whole setup for any of these binary acids. You start with the hydro prefix, the base name of the anion. So in this case, we have chlorine, bromine, sulfur, but replace the ending with ic acid. So HCl would become hydrochloric. So we changed chlorine to ic, and then we have to add acid. HBr would turn into hydrobromic acid. And that's coming from the base name of the anion, which is bromine. So we take away the ene, and same thing with chlorine. We take away the ene, chlorine, and we replace that with ic. And to indicate of those hydrogens, those donatable protons, we add ic acid. And then H2S, same thing. The anion there is sulfur. So this would be hydrosulfuric acid. So sulfur, that ending is a little weird. So we just call it sulfuric. We just add the ic ending on the end of sulfur, hydrosulfuric acid. And we call it this. We have the hydro beginning part because it's a binary acid. This changes when we get to oxo acids. Some of the names for acids look kind of similar, but they follow these same guidelines. Anything that starts with hydro is one of these binary acids where we only have one nonmetal anion present in the formula. It changes when we have a polyatomic oxoanion. So you might have heard of sulfuric acid or nitric acid. Those acids come from the polyatomics. So here, NO3, we know that that's nitrate. SO4, that's sulfate. We have phosphate, and SO3 is sulfite. So for naming polyatomic, an acid that comes with a polyatomic anion or polyatomic oxoanion, we want to name the anion. So see that sheet. And then, like in nitrate, you want to change the ate ending to ic acid. If it's an ite ending, like sulfite, then you change it to us, OOUS, that type of ending. So for example, if we do that here, HNO3, so if we identify NO3, that's nitrate. So HNO3, making it into an acid, turns this into nitric acid. We get rid of the ate and turn it into ic and tack on acid to indicate that there's a hydrogen present at the beginning. And also note, for many acids, we always put the hydrogen at the front of the chemical formula to show you like in your face that it's an acid. Okay, H2SO4. H2SO4. So if we look at our naming sheet, SO4 is sulfate. So follow the same rules. Take the base name of that oxoanion, so we're going to drop the 8 and just turn it into ic acid. So this would be sulfuric acid. So the next one here, H3PO4, make sure you can see this, H3PO4. PO4 is phosphate. So phosphate. This one's a little bit different. PO4 becomes, or phosphate actually becomes phosphoric. So we kind of added this or in there, phosphoric acid. I forgot a P in there. Phosphoric acid. But we still kind of follow that ic acid ending like in all the other ones. And then the last one, H2SO3. So SO3, I don't have room here. SO3, H2SO3. SO3 is sulfite. So if it has an ite ending in the oxoanion, we change it to OUS acid, acid. So sulfite becomes sulfurous acid. Okay, so those are oxoanion naming. And I think once we get into lab and start using acids within our in-person labs, you'll get the hang of it. All right, so let's do some examples in naming acids. So remember, acids fall under two categories. We have binary acids, where it's an acid or like a hydrogen just connected to one nonmetal, so like in these two examples. And then we have oxoacids, hydrogens that are attached to a polyatomic. So let's go through those. So these first couple are all polyatomics or oxoacids. So the first step is to always identify what is the polyatomic that it's attached to. So this is nitrate. So H tacking on a proton to make it an acid turns this into nitric acid. This is an oxo acid, so we follow this naming convention. It's just the base name with ic or us acid, not binary. Binary acids will always have the hydro prefix attached to it. Okay, so H2SO4, SO4 is sulfate. So this is sulfuric acid. So this one doesn't quite follow that rule. Sulfate, we added a in there, so this would have been sulfic acid, but it just rolls off the tongue better if we call it sulfuric acid. But the ic ending still kind of stands there. Okay, H2SO3. So SO3 is sulfite because it has one less oxygen than SO4. So this becomes sulfurous acid. H3PO4, I think we've done all of these. PO4 is phosphate. So this becomes phosphoric acid because it has that 8 ending. Right, here's a new one. H2CO3. So CO3 on our list, this is carbonate. So since this is an oxoacid, we just take away the 8 ending and turn it into ic acid because this is an acid. There's hydrogens there. So this is carbonic acid. This is what makes our soda pop fizzy, tasty. Carbonic acid. All right, HI. So this is a binary acid. So we need to use the hydro prefix. So if we identify the nonmetal that the hydrogen or the proton is attached to, this is iodine. So the rules there for binary acids is we always start with hydro, then you do the nonmetal base name. So this would be IO, but we drop the INE ending. We drop the ending and replace it with ic acid. So iodic acid, hydroiodic acid. Yes. All right, next one. So HC2H3O2. So C2H3O2, this is acetate. All right, and so it is also a oxo anion. It's a polyatomic, so it doesn't fall under our binary rule. So there's no hydro. So we just take the polyatomic name and add, or chop the end off and turn it into ic acid. So this would be acetic acid. Drop the 8 and added ic acid instead because it's a binary. Or sorry, because it's an oxo acid. All right, last one, HBr. This example is a binary. So we stick with the hydro prefix because it's binary. Identify the anion. This is bromine. So we drop the ene ending and replace it with ic acid. So this is hydrobromic acid. So there are a lot of examples with acid naming. Again, the big differences that you'll see here is we have binary acids, hydrogens that are just attached to a nonmetal or one nonmetal, so they all get that hydro prefix. And then we have polyatomic acids or oxo acids. And so in those examples, we do not use the hydro prefix, and it's just the base name of whatever anion is there with ic acid. So in both examples, you always see that we take the base name of whatever the hydrogen is attached to and then add ic acid or us acid in some cases. All right, so that wraps up naming. So I always like to include an extra credit opportunity for students who are consistent in watching lecture videos. So here's some extra credit naming. If you email me the answers to this, so turn these chemical formulas into names, and then turn these names back into a chemical formula. If you email me this, like screenshot it or something, and write it out to me, then I will give you extra credit on your midterm 1. All right, that's it, folks. See you at chapter 3.